Wow, so I forgot to record when I was doing this video, so this is my like third take. Wow, I'm actually really mad. Oh well. So welcome back to 16.7. We're still talking about Stokes Theorem. God. And this is a long video too, so I just wasted like 25 minutes. But anyways, welcome back to Stokes Theorem. We're recording definitely now. And yeah, so where were we? Well, in the previous video, we were asked to find this line integral, right? And instead, we said, screw that. We're not going to find this line integral because then we'd have to parametrize every line in our region, right? So here's that. We would have had to parametrize those three lines, and instead, we used Stokes' theorem, and we found the curl of f. We dotted it with n, and then we had d sigma as well. And then we just found that double integral, okay? So that was the previous video. In this video, then, we're going to be asked to find this guy, all right? We're going to be asked to find the curl of f dot n d sigma first. And the book, or, on the exam, it might be called the flux of the curl. So if you're asked to find the flux of the curl, then, in this video, I'm going to show you two methods. We're going to use this line integral to find the flux of the curl, or we're going to use independence of surface to find the flux of the curl as well. Okay, so there's two methods going to be presented in this video, and yeah, let's dive into it. So this is the problem. You're given a vector field f, and you want to determine the flux of the curl of f outward through the hemisphere x squared plus y squared. Is plus z squared equals 1, and we also have z is greater than or equal to 0. So what do I have then? Let's draw a region, x, y, z, and so we have a hemisphere, right, x squared plus y squared plus z squared is equal to 1, and then we have then, let's see, down here, right, we have where it intersects the xy plane, right, at z equals 0. So the green guy is my hemisphere, and then I got z equals 0, okay? And so essentially you want to find the flux, then the flux of the curl through the green region that I'm shading right now. And the reason is because, well, first of all, this is a hollow sphere, right? Because it's equals 1, not less than or equals to. So since it's equals, it's hollow. And then, yeah, we're trying to find the flux that like runs through that sphere, and not the bottom because, again, it's hollow. So one way to think about it, and there's a reason why I chose the colors this way, is you can think about it as a watermelon that you've hollowed out the inside of the watermelon. So now you just got the green shell of the watermelon, and then there's like a ring, this red ring here, which is like the lip of your watermelon shell. Okay? So that's one way to think about it. And so how are we going to do this? Well, method one, right, remember, was to then use the line integral, right? So what does that mean? Well, it means then that instead of finding curl of f dot n over the region, which is my watermelon, I need to find f dot dr, which is the line integral over c. And what is c? C is going to be the boundary, so over the boundary. Over the boundary. Okay, and well, so that means the double integral of curl of f dot n d sigma over the watermelon is going to be equal to the line integral of f dot dr, and it has to be closed, right? The boundary has to be closed. That's literally the first condition that matters. So the boundary C has to be closed, and that's why I have this circle. And over, well, what's the boundary of the watermelon, right? And it doesn't make sense initially. It's really hard to think about, but the boundary of the watermelon is not going to be this green shaded stuff, right? It's not going to be like this outside right here. That's not the boundary of the watermelon, because if you think of a bowl, right? Well, it's not like it ends there. Like, it's not like the bowl ends there. There's a whole like other side, right, of the bowl that we can't see because, well, my drawing sucks and because we're drawing two-dimensional stuff in 3 dimensions. But, right, so here's the watermelon again. Right, but what is the boundary? Well, if you think about a sheet of paper, right, like if this was our sheet of paper, we don't say the inside of the sheet of paper is the boundary of that sheet of paper. That doesn't make that doesn't make any sense, right? The area part of the sheet of paper is not going to be the boundary. But what is the boundary then are these 4 lines that surround the area, right? And you can think about it that way in terms of this watermelon as well. The surface area part right here, that I'm shading in green, that's not going to be the boundary. But what is the boundary then is going to be this ring right here that essentially cuts off where the surface area is, right? So I'm actually taking the double integral, this line integral over the ring, which is closed, right? Right, this is closed. And it's probably good then to find what the equation of the ring is. And since we're at z equals 0 on the ring, right, because we're taking the watermelon above z equals where z is greater than 0, then the ring has to lie where z equals 0, and so the equation of that ring is going to be x squared plus y squared is equal to 1. So, right, we want to find we're taking the line integral over that closed ring, x squared plus y squared is equal to 1. And now what I want to do then is we want to parameterize our boundary. Okay, so which is again the ring or the lip of the watermelon. that doesn't matter. And parametrizing the boundary. Okay, so what is r of t? Well, we have to parameterize it which way? Counterclockwise, right? We always have to parameterize it counterclockwise. So here's counterclockwise. And so counterclockwise has to be a parameterization. And remember, our region then is x squared plus y squared is equal to 1. And how do I parameterize that? Well, you really should know what this parameterization is, right? Because I actually think I mentioned in a video in like chapter 13 that you should know how to parameterize a circle. And in 16.1, you should have gotten a lot of practice with this. But to parameterize a circle then of radius 1, it's cosine t, sine t, and then we need our z coordinate, but we're at z equals 0, right? So, yeah, and this is the counterclockwise parameterization of a circle. Cool. Now we need to find what f of r of t is. Well, f was y plus root z, e to the xyz cosine xz. So y plus root z becomes sine of t plus root z is 0. All right. E to the xyz, well, x times y times z is going to be 0 since z is 0. So that's e to the 0. And then cosine xz is going to be cosine 0, right, since z is 0. And so that's really then sine t, comma 1, comma 1. Okay? And now what? Okay, so that's f of r of t. Now I need to find r prime of t. Oh, wait. Quick backtrack. For r of t, we need our t-bounds, right? And what are they going to be between? Well, our t-bounds are going to be between 0 and 2 pi, right? Because that's how we parameterize a circle. Okay, now r prime of t, what is r prime of t? Negative sine of t, cosine of t, 0. All right, and now the double integral over of curl of f dot n d sigma over our surface then is going to be equal to the line integral of f dot dr over my curve or the boundary, and that's the same then as f of r of t dotted with r prime of t dt, right? And yeah, right, f dot dr, I guess I didn't mention that, but it's f dot dr is f of r of t dotted with r prime of t, 16.2 stuff. You should be familiar with this. And now what? So now that means we have the integral of f of r of t is sine t, comma 1, comma 1, dotted with negative sine t, cosine t, 0, dt, and we're going from 0 to 2 pi. which is our t-bounds, and then this becomes in the integral from 0 to pi of negative sine squared t plus cosine t, all right, dt. And if you do this integral, if you split it up, right, negative sine 2t, sine squared t, not 2t, sine squared t, plus the integral of cosine t, right? This integral is going to be 0, and this integral, this first guy, you need to use the fact that, well, pull the negative sign out in front, and then you need to use this fact that this is negative, this is 1 minus cosine 2t over 2, which is what sine squared t is equal to, right? But got to pull that negative sign out first. And then, yeah, if you do that integral, you'll get negative pi as your answer, okay? So that means the flux of the curl over the watermelon is equal to negative pi. And what are the highlights of this? Again, since we're going backwards, we can evaluate this integral as a line integral over the boundary. And we said the boundary was the ring. The boundary is closed, which is very important. And then we found x squared plus y squared is equal to 1, okay, which is the equation of the boundary. And then we have to parametrize it, knowing that z is equal to 0, because that's where my boundary is, right? It's in the xy plane at z equals 0, which is given in the problem. And then, so we parametrized it. Counterclockwise is another big deal. You have to parametrize it counterclockwise. And then, right, so the line integral f dot dr is f of r of t dotted with r prime of t, which I didn't mention initially, but you should have caught on. And so you find those guys, plug it into your integral, and you integrate, and you're done. All right, so very quick. Well, kind of quick, but this is how you then do these types of problems, or that's one way you can do these types of problems when you're asked to find the curl of the flux of a curl, right? The flux of a curl. So what's the next step? The next step then is method 2. Method 2, it's independence of surface. And the idea is this. If I have a double integral of curl cross f dotted with n, let's say n1, d sigma, and I'm over one surface, S1, all right? It's equal to the double integral over S2, a different surface, of curl of f dotted with n2, so this is just the normal corresponding to this new surface, d sigma, where, when, or if, boundary of S1 is equal to the boundary of S2. Okay? So the curl of f dot n d sigma is equal to the curl of f dot n d sigma over another surface if the two surfaces share the same boundary. So in our case, right, S1 was the watermelon. So what should we choose for S2? Let's go back up here, right, to this picture. What should we choose for S2? So I'll let you think about it for a little bit. Okay, well, S2, if you said we should choose some light bulb as S2, then you are correct, right? Because we can choose any surface we want. No, definitely not, right? Because remember, we're trying to find a curl of f dot n d sigma, and what is n of this light bulb? Well, who the fuck knows? Because you need to parametrize this fucking light bulb. So no, don't choose that light bulb. Don't be stupid. Choose a surface that makes sense, okay? And the surface you guys probably all chose that shares the same boundary as the watermelon, which is very clear from this picture, is going to be this disk in the xy plane, right? Let's choose the disk in the xy plane. And why is that? Well, we'll see why. So we're going to choose this disk in the xy plane. So choose the disk x squared plus y squared is less than or equal to 1, right? Why is it less than or equal to 1? Well, the boundary is equal to 1. So if you want if we want the yellow guy on the inside, then that has to change to a less than or equal to sign, right? So choose the disk x squared plus y squared is less than or equal to 1 at z equals 0. as S2, okay, which is the yellow disk. Okay, and now what do we want to do? Well, now we need to find each component. So we need to find the curl of F, we need to find N2, and we need to find d sigma. All right, so bear with me here. I'm going to actually find N2 first, or just N in our case, right? We don't have to call it N2 since we're never finding an N1. What is N? Let's look at this picture. Let's think about it. What is the normal vector to the disk, the yellow disk? Well, the yellow disk is in the xy plane, right? And if we're in the xy plane in 3 dimensions, then the outward pointing normal is always just going to be that guy, right? It's always just going to be 0, 0, 1, pointed in the direction of z, right? I mean, we talked about this for a really long time in the surface area stuff, right? When we were asked to find an implicit integral, or the implicit surface area, we had to find what p is, right? P was the normal vector. And I said repeatedly that if P is, if you're in the xy plane, then P is going to be 0, 0, 1, right? So since this disk is pretty clearly in the xy plane, then my normal is going to be 0, 0, 1, okay? All right. Okay, cool. And now what? Well, now let's find the curl of F. Okay, which is ijk, right? ddx, ddy. This is the upside down triangle vector, or del. This is the del vector, the partials. And then f was y plus root z, e to the x, y, z, and I forget the last one, cosine xz. Yeah. Okay. Okay. Now what? Well, now this is equal to, well, what is this equal to? Well, let's think for a second. What am I trying to find eventually? I'm eventually, after we find d sigma, right, I'm going to set up this integral, curl of f dot n, d sigma, right, which then is going to be the double integral of the curl vector dotted with n, right, and then whatever d sigma is. But what is n? N, we already found, is 0, 0, 1. So when I'm finding curl, well, whatever this guy is, it's going to get dotted with 0, right? It's going to multiply by 0. So that's going to end up being 0. Whatever this guy is, it's going to get multiplied by 0. So that's going to end up as 0. So the only guy that actually matters in the curl vector is going to be this last guy, right? Because it's going to get multiplied by 1. So that means that I can just ignore these first two. No one gives a no one cares what these guys are. And that means I just need to expand then on this last guy to find the last entry. And what do I get? This looks like it ends up being the partial of x of this guy, which is yz, e to the xyz. And then the partial y of that guy, so minus that is minus 1. All right. So again, I only need to care about this last entry because eventually when I'm dotting with n, right, when I'm dotting my curl with n, everything gets sent to 0. The first two components get sent to 0, but the last guy gets multiplied by 1. Okay? So, all right, this is what I get. But remember, we're at z equals 0, so I need to plug in z equals 0 here. And that makes me end up at some question mark, and then if you plug in z equals 0 into this guy, you get 0, right, because that's y times z. So then you get negative 1 as curl of f, all right? So some question mark, and negative 1. Don't actually have to find what they are. Saves a lot of time and, possibilities of errors. And then now we know to find d sigma, but let's consider for a moment what is d sigma, right? So remember from 16.5 that the double integral of d sigma is the surface area, right? So what are we integrating over? We're integrating over the lid, right? We're integrating over the lid, this yellow lid up here. What is the surface area of this yellow lid? It's just the area of the lid, right? And the surface area is just the area. And that's because I'm in a two-dimensional space, right? My lid is in the xy plane. The xy plane is a two-dimensional space. So I just need to, like, if I parameterize, like, the circle, it's just going to be, like, dx dy, right? Or that's going to be my area thing for the lid. So d sigma is going to be dA since we're in the xy plane, which is a two-dimensional space. Right? The xy plane has two dimensions, has the x dimension, has the y dimension. So, but in general, right, d sigma, like for this watermelon is obviously a surface in three-dimensional space. It's a bowl, right? And so d sigma over the bowl, and then it's going to be something fancy, but because the bowl is 3D, but d sigma on this disk, a two-dimensional disk, well, that's just the area of the disk, right? So very easy to find. So again, because we chose a smart S2, the normal vector and d sigma are really easy to find. So now what? So now this dot product, right? So this is curl of f dot n d sigma. We have curl of f, we have n. So d sigma is really just dA. Okay, so now this dot product becomes, this is -1. Whoops, right? Or whoops, that's 1. This is -1. I need to fill in. So curl of f dot n, so this becomes -1 dA. Okay? And so that's actually equal to -1 times the double integral of dA. And so now let's consider, what is the double integral of dA, right? Well, from chapter 15.4 or 15.3 or whatever, we're just trying to find the area of a region, right? We're just trying to find the area of a region, the double integral of dA. Well, we know the area of a region, right? What is a region? Our region is this yellow disk in the xy plane, right? That has the equation x squared plus y squared is less than or equal to 1. Right? Did I write down? X squared plus y squared is less than or equal to 1. That's the area. That's a region. And we know how to find the area of this guy. It's a circle, right? And what's its radius? The radius is 1. So instead of actually parametrizing and trying to do this integral, we can just say, oh, this is -1 times the area of my region, right? Which is -1 times pi r squared, which is -1 times pi, and so our answer is -pi, and voila, that's the exact same thing as what we found with the line integral. So independent of surface, again, what are the highlights? If S1 and S2 share the same boundary, then I can just find curl of f dot n d sigma over this new surface, S2. And in our case, right, the green guy, the watermelon shell, as this first surface, and the second surface is going to be like a lid or like a disc covering that watermelon shell, okay? And so that's the yellow guy. That's the second surface. And the reason why I chose that second surface is because, well, the normal vector is really easy to find since we're in the xy plane, right? So the normal vector is 0, 0, 1. So I chose a smart second surface, makes the normal vector easy to find. That means for my dot product, that's going to kill whatever's in these first two components of curl, right? And that means I don't have to find them. I only need to find the last component of curl. And then I need to remember I'm at z equals 0. Because that's where my disk is. That's where my region is, right? This disk is lying in z equals 0. Larry says right there. And that's because that's just the surface we chose, right? It's this yellow disk. It's at z equals 0. And now, what else? D sigma is equal to dA because we have a two-dimensional space. And if you think about it, right, what's the surface area of that disk in the xy plane? Well, that's the exact same thing as the area of the disk in the xy plane, right? So then this double integral of the lid or the disk, I mean, I've been calling it interchangeably the disk and the lid, becomes the double integral over curl of f dot n d sigma, which ends up being -1 times dA. Well, if I factor out that -1, it becomes -1 times the area of my region, and I don't even need to calculate the area of my region using an integral, because I know 7th grade geometry, and I can just say it's -1 times pi r squared, where r is 1 because of the equation, right? X squared plus y squared is less than or equal to 1. So this is the radius squared, which is 1 squared. And then negative 1 times pi r squared is, well, pi 1 squared is equal to negative pi. We find an answer, which is the exact same thing as the line integral answer. So, okay, what did we do in this video? We were asked to find the flux of the curl, all right, in the question. That's what we were asked to find. However, we ignore that, and we either use this line integral over the boundary, right? And it has to be closed. Remember, the boundary has to be closed. Or we used independence of surface, where we chose a different surface to calculate this guy. So that is Stokes' theorem in a nutshell. And that should be enough to get you guys through a lot of Stokes' theorem problems. It's very important that you understand what's going on, because Stokes' theorem is guaranteed to be on the exam. Like, guaranteed to be on the final. So, yeah, study it hard. Do Stokes theorem problems as much as you can. These two are pretty much the only types of problems that will show up in these previous two videos. And yeah, so that's it for Stokes theorem. We're going to move on to 16.8, the final section. And thank God I actually recorded this, so I don't have to do this for a fourth time. These are long videos.